Hello and welcome to another video discussing fluid mechanics. Today's topic is fluid statics. So let's start with type of forces that act on a fluid element. Now, generally speaking, we have surface forces and body forces acting on a fluid element. Now, body forces are the ones that are applied to the bulk or the mass of the fluid element. A very well-known example of a body force is gravity. It is applied on the mass of the fluid element. Any other force that is not a body force is surface force. Examples are pressure and shear stress. Now in this video, we are discussing fluid statics. Now we know that in statics, we have no motion. No motion means no velocity gradients, which in turn means no shear stress. Because remember, shear stress on a fluid element is directly related to the rate of deformation of the element or the velocity gradient inside the flow. So no velocity gradient means no shear stress, and so surface forces in a case of fluid statics is reduced to pressure only. Now let's talk about the body force, gravity. So for a fluid element that I'm drawing here, let's assume that this cube is a fluid element. These are the dimensions. Let's say this is the x, this is the y, and this is dz. So I can say the body force due to gravity, I'm going to show it with df of b, meaning that it's a body force, is gravitational acceleration times the mass of this fluid element, right? Now, we know, generally speaking, force is a vector, and g, gravitational acceleration, is a vector. So dfb as a vector is g as a vector times dm. I can manipulate this equation a bit further. Instead of dm, or the mass of the element, I can say rho, the density of this element, times dv, the volume of the element. Now, for a fluid element that looks like a cube like this, I know that the volume is equal to dx times dy times dz. So putting these two equations together, I can conclude that the body force due to gravity on this fluid element is g rho dx dy dz. So this is the body force acting on this fluid element. So we decided that pressure is the only form of surface forces acting on a fluid element in fluid statics. All right, so let's revisit the fluid element. This is the fluid element that we are interested in. I'm trying to draw all 6 faces here. Now let's put a coordinate system next to this element so we know what's going on. This is our coordinate system. This is y, this is x, and this is z direction. Based on this coordinate system, I can put some dimensions on this element. I can say this is the x, this is the y, and of course, this is the z. Now, let's say we know the pressure at the center of this cube. This cube element is our fluid element, and we know that the pressure at the center is P. Now, using the Taylor series, I can find the pressure on all 6 sides of this cube element. So let's focus on these 2 faces first, these ones that I'm coloring orange. And let's call them the left and right plates. I'm going to call this one left plate and this one right plate. Now, pressure on the left using a Taylor series can be written as P on the left is equal to the P of the center of this cube minus partial P partial Y dy over 2, right? This is how you use a Taylor series to find the pressure on the left side of this cube. I can do the same thing for the pressure on the right side. So pressure on the right is going to be the pressure of the center of the cube plus partial P partial Y times dy over 2. Now, of course, I know that the force in the y direction, I'm going to put an S here to show that this is the surface force in the y direction, is going to be PL minus PR times the area of the element. I get, let's plug in the values in this equation. I get P minus partial P partial Y dy over 2 minus P minus partial P partial Y dy over 2 times dA. So the area of these orange surfaces is dA equals dx dz. They're just normal rectangles. One side is dx, the other side is dz. So obviously the area will be dx times dz. So I can plug that into my surface force in y direction equation. I can get df surface in y direction is equal to, now take a look at the equation here. So p's cancel each other. This p cancels this guy. And I get negative partial p partial y times dy times dA. Now from here I know dA is dx times dz. So I can say df surface in y direction is negative partial p partial y dy dx dz. So I found the surface force, at least in y direction, as a function of pressure. I can have the same approach for the 4 remaining sides of this cube and find equations for forces in x and z directions, respectively, as functions of pressure. Now, if I do that, I will get dfs in vector form is negative partial p partial x in y direction plus partial p partial y in j direction plus partial p partial z in k direction times dx, dy, and dz. Now this term here is very interesting. This is the gradient vector of a scalar field. You have to remember that pressure is a scalar, and this is the gradient of that scalar field. We call this the pressure gradient. And we usually show it like this. So just to be clear, gradient of P, we show it like this, is equal to partial P partial x in I direction plus partial P partial y in j direction plus partial P partial z in k direction. So now I can say the surface forces acting on my fluid element are negative pressure gradient times dx, dy, dz. So total force acting on my fluid element was supposed to be the body forces plus the surface forces. So let's plug in the expressions for body force and surface force into this equation and see what we get. F is negative pressure gradient plus rho g dx dy dz. Now we have to come back to our first assumption of this topic, and that is we are talking about fluid statics. So fluid statics means no motion. Now we know from Newton's laws of motion that if an object, a fluid element, a solid particle, is not moving, that means the sum of all forces acting on it are zero. So I can conclude that dF, forces acting on my fluid element, is zero. This immediately gives me negative pressure gradient plus rho g is zero. Keep in mind that pressure gradient is a vector. Now keep in mind that this is a vector equation. So in a 3D space, let's say in a Cartesian coordinate system, this vector equation gives me a system of 3 equations. Let's check them out. So far, I have not made any assumptions regarding the direction of the gravitational acceleration. Now, let's say this is my coordinate system, this is y, this is x, and this is z, and this is again my fluid element. Now, gravitational acceleration in a scenario like this is in the direction of negative z. Okay, so I can say that the vector g is negative gk. Now, with this piece of information, I can write these 3 equations that are hidden inside that vector equation. The first one is in the x direction. I have negative partial p partial x plus rho gx is equal to 0. Now, gx represents the x component of the g vector. The second equation is negative partial p partial y plus rho gy is equal to 0. Again, gy is the y component of the g vector. And finally, negative partial p partial z plus rho gz, the z component of the g vector, equals to 0. Now, looking at the g vector here, it only has a z component, meaning that gx and gy are 0. So from the first 2 equations, I can conclude that partial p partial x is 0 and partial p partial y is 0. This is a very important conclusion. It shows you that in a static fluid, when there is no motion, pressure does not change in the x and y directions. In other terms, pressure is independent of x and y coordinates. Now, what about the z direction? Gz, or the z component of the g vector, has some value. So let's plug that here in this equation. I get negative partial p partial z rho g is equal to 0, or partial p partial z is equal to negative rho g. Back to our previous conclusion, we concluded that because of these 2 equations, p is not a function of x and y. With that condition in mind, I can change the partial differentials to ordinary differentials and conclude that dp dz is equal to negative rho g. Again, a very important conclusion, showing that in a static fluid, pressure changes in the direction of gravitational acceleration, in the direction of g. Now let's see what we can do with this equation. So I can have a few different scenarios going on here. The first scenario is when we are dealing with an incompressible fluid. Now, an incompressible fluid is a fluid where the changes of density is negligible, or in other terms, density is a constant. If we are dealing with such fluid, like most liquids, then we can say, okay, dp dz is equal to negative rho g, and then I can say, all right, dp is negative rho g dz, and then I can make the integral saying that the integral from p0 to p of dp is equal to the integral of negative rho g dz from z0 to z. That gives me p minus p0 is equal to negative rho g z minus z0. Now I can play with the negative sign here and say, okay, p minus p0, I'm going to call it delta p, is equal to rho g z0 minus z. Or I can rename this z0 minus z and call it h, and so I can conclude that delta p in a static fluid is equal to rho g h. Now this is the equation that we generally use to find the pressure changes inside a liquid, and usually we use this equation when we want to read the pressures in manometers and barometers and stuff like that. Now I have a video, I have actually 2 videos dedicated to that topic. I'm going to put the links down in the description, so I'm not going to go through the topic of finding the pressure using a manometer. If you're interested in that topic, you can check the links down in the description below. Now let's see what other scenarios we might have. So incompressible fluid, generally speaking, covers the liquids. How about gases? Let's say we are dealing with ideal gases. Now from the ideal gas equation, we know that pressure is equal to density, gas constant, absolute temperature of the gas, right? So let's see how we can plug that into our main equation. I know that dp dz is equal to negative rho g. From the ideal gas equation, I can say rho is actually p over RT. So let's plug that here. Negative p RT g. Now I need to separate the variables. I need to bring the p from right hand side to the left hand side and move dz to the right hand side. Doing so gives me dp over p is equal to negative g over RT dz. Now, the only way that I can make this integral now is that the temperature is not a function of z, or pressure. Generally speaking, g, gravitational acceleration, is a constant, so no problem there. R is the gas constant, again a constant number, so no problem there. The only other variable besides pressure and z is temperature T. Now again, if temperature is not a function of either elevation z or pressure p, then I can make this integral and say, okay, natural log of p over p0 is equal to g over RT h. Again, h is z0 minus z. Now this equation, again, is generally acceptable when dealing with ideal gases on nearly all of engineering applications, like day-to-day applications that we deal with. However, you have to be extra careful when discussing the pressure changes of air in atmosphere. Now, in atmospheric studies, the temperature of air changes with regards to elevation. So T in those studies is a function of elevation, and then you need to know that function in order to making this integral. Let's talk about the hydrostatic forces on submerged surfaces. All right, so let's start with analyzing the forces on a plain submerged surface or a flat submerged surface. Let's say this is the liquid surface. For the sake of this example, let's say this is the water surface. And in order to show the liquid or water or fluid surface, we usually use this triangle with three lines below. This shows that we are talking about the free surface of a liquid. We have a wall down there. There is a plate sitting here submerged in this liquid, right? We are interested to find out the forces that are applied on this plate by the liquid. So now a few useful parameters here. This angle here is theta. Now I can say that the coordinate system I'm using looks like this. This is the y-axis and this is the z-axis. Now the x-axis is normal to this paper. So let's take an element on this plate and start to analyze it. So this green rectangle here is our element on the plate, and we're going to analyze the forces acting on this element. So first thing first, we know that the pressure, the force of the pressure is always normal to any surface. So the force acting on this element is going to be normal to this plate. I'm going to call it the F. Now the depth of this element, this green element, with respect to the free surface of the liquid, I'm going to show it with H. So H shows the depth of any element on the plate with respect to the free surface of the liquid. What I'm looking for is the total force acting on this plate. Now, let's take a look at this plate from another angle. The area of the plate can be arbitrary. The shape of this plate can be arbitrary. As you can see, I drew a completely arbitrary shape as the shape of my plate. To give you a perspective, this is still the y-axis, and this is now the x-axis when looking at the plate like this. Okay, so the elements that we took on this plate, the green element that we took on this plate, looks like something like this. So its area is dA, its dimensions are dx and dy. So this is the element on this plate that I am interested in. Now again, we are talking about the forces in a hydrostatic situation, meaning that there is no motion. In this case, we know that all the forces working on this element, on this plate, are the pressure forces or surface forces. So dF is just dA. So the total force that we are looking for, Fr, is going to be the sum of all these tiny dF forces, right? It will be the integral of dF over area A. Area A is the area of the plate of this random arbitrary area that we have here. This is integral over area of pressure dA. So far, so good. Now we need to know how the pressure changes. So based on what we know so far, we know that the pressure at any given depth inside a liquid is rho g h plus, of course, the pressure of the atmospheric air outside the liquid. Let's say here we have air and it has a pressure of its own. We call it P0. So the pressure here on the green element is going to be the pressure of the air, P0, plus the pressure of the column of the liquid on top, which is rho g h, right? So pressure is rho g h plus P0. What is the relation between h and y? Now, if you take a closer look at the drawing on the right, you can probably guess the relation. H is y sine theta. Now, y here is the coordinate of the green element on the y-axis. In order to find the h, or the depth of this element, you have to multiply y by sine theta. All right, now let's see how we can combine all this information together and get a single expression. All right, so I can say total force is the integral of P0 plus rho g. Instead of h, I'm going to write it y sine theta dA. Now I'm going to break this integral into two. I'm going to say total force is the integral of P0 dA plus the integral of rho g y sine theta dA. Now here's the interesting part. P0 is the pressure of air outside the liquid, so it's constant. So it can jump out of the integral. For the second integral, we're talking about the liquid, right? So density can be treated as a constant. G is the gravitational acceleration, so it is a constant. Sine theta is a constant because the angle of the submerged surface is not going to change. So these three terms can jump out of the second integral. With that in mind, I can say that the total force is P0 times the area of the flat surface plus rho g sine theta integral of y dA. Now, integral of y dA over any surface, any area, is an interesting integral. This is the first moment of area. We know that the integral of y dA over an area is equal to the y of the centroid times the area. I get that total force is P0 A plus rho g sine theta YC A. This is a good equation, but we are not done yet. All right, so back to our initial sketch. This term here, YC times sine theta, what is that? Now, YC is the location or the y component of the centroid of this plate. Somewhere maybe here. Maybe this is YC. Now, YC times theta is the depth of the centroid of this plate. We can show that with HC. Fr, the total force that a submerged flat plate is experiencing because of the fluid above it, is P0 plus rho g HC, the depth of the plate's centroid, times its area. This is our final equation. We can go ahead and simplify this equation one more step. It's not crucial, it's not mandatory, but we can do it. The term in the parentheses, P0 plus rho g HC, actually represents the fluid pressure at the centroid of the plate, right? So, Fr, total force, is the pressure of the centroid times area. Now, if you're not comfortable or familiar with the concept of centroids, I would strongly suggest to review your notes from the course Statics. Okay, so we found the magnitude of the total force. Now we really want to know where this total force is applied to. So I know that the total force Fr is P0 plus rho g h of the centroid times the area, right? Now I want to know where this force is applied to. Let's say the location that I'm looking for is y prime. So Fr, the total force, is applied here on y prime, right? And I want to find it. So again, this is a trick that we learned in statics. In order to find y prime, I can use this following equation. I'm not going into the detail of how to achieve this equation. It is discussed in details in statics. Here, I'm just going to use it. Y prime times Fr is equal to the integral of y df. This is actually y p dA, because remember df is pdA. The integral is made over the area. Y prime times Fr is the integral of y times the pressure at any element dA on this area. We discussed that in previous pages. So it's y times P0 plus rho g y sine theta dA. Playing with this equation gives me integral of y P0 dA plus integral rho g y squared sine theta dA. Now again, P0 is a constant, so it can jump out of the integral. Rho, g, and sine theta are constants as well, so they can jump out of the integrals as well. Let's see what we can get. So y prime times Fr is equal to P0 integral of y dA plus rho g sine theta integral of y squared dA. Again, we have very important integrals here. Y dA, the integral of y dA is equal to y of the centroid times area. So far, so good. What about integral of y squared dA? What is this? Now, this is the second moment of area about the x-axis. This is Ixx. Again, this is something that you learned in statics. However, this is not really optimal for us yet, because this second moment of area is about the x-axis, which we defined was tangent to the free surface of the liquid, right? We really want to express this equation in terms of centroidal axis. So I'm going to use the parallel axis theorem. Now the theorem states that the second moment of area about the x-axis is equal to the second moment of area about the centroidal x-axis plus area times yc squared. Okay, again, this equation comes from static. Let's combine these two and see what we can get. So I get y prime Fr, which is the total force, remember, is equal to P0 YCA plus rho g sine theta, second moment of area about the centroidal x-axis, plus area times yc squared. That means y prime is P0 yc area over Fr plus rho g sine theta Ixx over Fr plus rho g sine theta yc squared over Fr. Now I'm going to add these two terms into a single fraction. So I get y prime is P0 plus rho g. Now, sine theta times yc is hc, right? Times area over Fr, the entire thing, times yc, plus the other term, rho g sine theta over Fr Ixx. Now remember that Fr, the total force, was P0 plus rho g hc times area, right? So this fraction is 1. And we get that y prime, the location of this total force, is yc plus rho g sine theta over total force Ixx. The second moment of area about the x-axis that goes through the centroid of your area. So this was the equation that we were looking for. These two equations on this page show you both the magnitude of the total force and the location of this total force for a plane submerged surface based on the absolute value of the pressure. However, you may be interested in the net force that is applied on this plate. What I mean by that is, remember our geometry? This was the free surface, this was the wall, this is theta, and this is the plate we are interested in, right? So we developed this idea that P0 is the atmospheric pressure. What is happening on the right side of this plate here? If this area is also exposed to atmospheric pressure with the pressure P0, then the net force applied on this plate is the sum of two forces. The total force that is applied because of the liquid and the air above the liquid on the left-hand side of the plate, and the force because of the pressure P0 on the right-hand side of this plate, right? So if the atmospheric pressure is the same above the liquid and on the right-hand side of this surface, then we can simplify these equations a bit. So for this case, I can say, okay, the net force is going to be total force of the liquid plus atmosphere minus the force of atmosphere. I'm going to call it F for simplicity. So P0 plus rho g hc times A, which is the Fr, the liquid, minus, now F here is going to be P0 times A, because the pressure of atmospheric air is constant. So P0A. P0A cancels P0A, and you get that net force is rho g hc times area. We can do a bit of algebra on the location as well. I'm not going to do it in details. I'm just going to give you the final answer. Y prime reduces to yc, the y of the centroid, plus Ixx over area yc. Now, if the other side is not exposed to P0, it's exposed to some other sort of pressure, then you have to find the net force and the location of the net force using the methods that you learned in statics. So now let's discuss the hydrostatic forces on a curved submerged surface. So we will have a situation like this. Again, this is the free surface of the liquid. And at this time, instead of a flat surface, let's say we have geometry that looks like this. Now this is in two-dimensional because I wanted to draw it here. You can, of course, generalize this method to three-dimensional as well. So this is a curved submerged surface. I'm going to again take an element on this area. The force working here is again going to be dF. Now, we know that generally speaking, dF or force is a vector, and we know that it is negative p dA. Now, the left-hand side of this equation is a vector, so it only makes sense that the right-hand side is also a vector. Now, pressure is a scalar. We know that much. So the only other variable that is left to be a vector is area. So area is also a vector. This is a very important note here. Area, generally speaking, is a vector. It has a unit vector and it has a magnitude. The magnitude of the area vector is equal to the magnitude of the surface area. The direction of the area vector is always normal to the plate of the area, is always normal to the surface of the area, and it's always pointing outwards. So now I can say, okay, the total force, Fr, which I am looking for, is the integral of dF, right? Which is the integral of negative p the area. This means that the total force is going to have three components in a general 3D space in the form of Fr, x in I direction, plus Fry in J direction, and of course Frz in K direction. We know that each of these are the components of the p integral. So this is actually the integral of p dAx, the x component of the area vector. This is the integral of p dAy, the y component of the area. And of course, this one is the integral of p dAz, the z component of the area. Now, what are these x, y, and z components of an area vector? So if this is the area vector, dA, then like any other vector in a 2D space, like the one that I'm drawing here, it will have two components. dA y, for example, and dA x, if this is the coordinate system that we are using. So dAy is actually the projection of area on the y-axis. The same logic, dAx is the projection of area on the x-axis. Now let's see how these projections can help us make these integrals. So if, again, this is a submerged curved surface like this, I can say, okay, I'm first interested in the horizontal or the x component of the total force. As we discussed last page, we can use the projection of the area, the x-axis, right? However, remember that the area vector is always normal to the surface. So we are actually looking for the projection of the area vector on the x-axis. That means the actual area we are looking for is the projection here. So this red line here is AX. or the x component of the area, because its normal vector looks like this. So for the horizontal force, we can just assume we have a plate, we have a flat plate with the area AX submerged in the liquid. And we can find the FRX, the x component of the total force. For simplicity, I'm going to just call it FH, the horizontal force. And from previous pages, you know that that is equal to PC area, where C is the centroid of the area. So finding the horizontal force is relatively easy. Again, you want to find the force on the projection of this curved area on the x-axis. By projection of the area on x-axis, we actually mean the projection of its normal vector on the x-axis. This vector is the projection of the area vector on x-axis, right? It represents this red line, this red bold line, the area of a flat plate submerged in this liquid. So finding the x component or the horizontal component was rather easy. Let's see what we can do for the vertical component of the total force. So finding the y component of the total force is a bit more tricky. Let's start with an area element like this. This is the A, right? We are interested in the projection of this dA on the y-axis. So I'm actually looking for the force acting on dAy. Now I'm going to zoom here so that you know what's going on. So this is the actual element, and this is its projection on the y-axis. Now keep this element in mind, the green element in mind, and let's continue with our analysis here. So the force, the vertical force, I'm going to show it with FV, meaning vertical force, is the force that this green element is experiencing. So what is that? dFV is equal to the pressure times dAy. So what is the pressure? The pressure, we know, is P0 plus rho G Y, where Y is the Y component of the green element. So the total force, vertical force, is going to be the integral of dFV, which is the integral of P0 plus rho G Y, the area. Now Y dA gives you the volume of this red element here, right? This is a element with a cross-section area of dA and a height of y. Its volume is going to be its cross-section times its height, which is dA times y. So the total vertical force is P0 AY plus the integral of rho G d volume. Now rho and G are constants, so they jump out, and the total force is going to be P0 AY plus rho G the volume. Now, two things to remember from this equation. AY that shows in the P0 term is this area, the projection of the curved area on the y-axis. The volume that shows here is the volume of the liquid on top of the curved surface. So the vertical force is P0, the atmospheric pressure, times the projection area, AY, plus the weight of the liquid on top of the curved surface. All right, so now let's talk about the final topic of today, buoyancy. So let's say we have a liquid, this is the free surface, and then I have an arbitrary object submerged inside this fluid of mine. It has a volume V. I am measuring the depth from the free surface with h, and of course the gravitational acceleration is in the direction of h. Now inside this arbitrary volume shape that I took inside the fluid, I am going to take a cylindrical three-dimensional element. Now this element has a volume dV, and the cross-section area of this element is dA. The top of this element is h1 deep. The bottom of this element is h2 deep. If this is the z direction, I want to know what forces are acting on this orange blob in the z direction. dFz, which is the force acting on this cylindrical element in the z direction, is going to be the pressure at the bottom, let's call it 2, minus the pressure of the top, P1, times dA. Of course, you know that, let's say you have a cylinder, like this blue element, and you have submerged it into the liquid, and you want to know what forces are acting in the z direction, in the direction or the opposite direction of the gravitational acceleration. Now, you know that in a situation where we're dealing with a hydrostatic fluid, the only surface force acting on your fluid element is the pressure. That's why I know that it will be P2 minus P1 dA. Now let's expand that equation. dFz is going to be P2. What is the pressure at location 2? It is P0 plus rho g h2 minus the pressure at location 1 is P0 plus rho g h1. The entire thing times dA. Obviously, P0s cancel each other, and we get that dFz is rho g h2 minus h1 dA. Now, something very interesting. h2 minus h1 is actually the height of this blue element, right? I'm just going to call it h3. So h2 minus h1 is h3, the height of the element. Now, height of the element times the cross-section of the element is the volume of the element. So I get that dFz is rho g d volume. Of course, you can make the integral over the volume of this orange blob, and you get that Fz is equal to rho g volume. Now, this Fz shows the force that the liquid is applying on this orange blob, on this orange object. This is called the buoyancy force. Now, this is the force that the fluid is applying onto the object. The weight of the object is independent of the buoyancy force. It's because of the gravitational acceleration, and it's independent of this. Now, depending on the relation between the buoyancy force and the weight of the object, we will have two general situations. Now, first, if the buoyancy force is, I'm going to show it with F of B, is greater than the weight of the solid object, then the solid object will float. If, however, the buoyancy force is smaller than the weight of the object will obviously sink. Now, as you can see, the buoyancy force is given in a form of rho g v. In this equation, rho is the density of the liquid, or for the fluid, right? We can write the weight of the solid object in the same shape. I can say, okay, W is mg, we already know that. But then I can play with the m and say it's rho of the solid, volume of the solid, g. Here, rho s is the density of the solid. Now these two equations are comparable easily. V, volume term, in both of these equations is the volume of the solid object. G is the gravitational acceleration, and so only density is different between them. So I can say that the net force acting on this solid object is going to be the buoyancy force minus the weight, which is G times the volume of the solid, rho of the liquid, minus rho of the solid. Like always, thank you for staying till the end of this video. If this video helped you in any way, I would appreciate it if you could leave a like or a comment and maybe subscribe for future videos. Thanks again and see you in another one.